Okay, last time well, let me first just refresh your memories on what we're doing now. We finished this long section on electricity and magnetism, and of course last year we learned all about gravity. So you've heard a lot about the forces of nature that scientists have discovered, but I haven't told you much about, there's another major topic that we haven't talked much about, and that is, what is matter exactly? I mean, what is the structure of matter? What is all this stuff that we see around us? And that's what I want to get to now. And what I want to end up convincing you of is that matter is made of atoms, and at the end of this course we'll learn just a little bit about the structure of atoms. But the first evidence of that comes from chemistry. And so we need to go into the whole science of chemistry now, and I mean that is the science that studied materials and what things are made of. I mean, one of the things that struck people as they looked around the physical world was there's a lot of different kinds of materials that undergo a lot of changes, and the attempt to understand that and investigate it did become the science of chemistry eventually. Now, at first, people just discovered bits and pieces of knowledge. They didn't have a science, but they developed a certain amount of practical knowledge just in working with materials. And I told you last time that very early on, they discovered how to, they discovered 7 different metals and how to get those metals in pure form from the ores that are found in nature. So the metals they knew about, and this is from your, probably already in your notes from last time. Let's see if I can remember all 7 here. Gold, silver, copper, lead, tin, iron, and what else? Anybody know? Mercury. Mercury always struck them as a very special element because it was the only, of course, the only one of these metals that was a liquid. And I started telling you about when one of the other elements of practical knowledge that was discovered very early on was some dyes that could be used to dye cloth for clothes. And so at the end last time I told you they had found a blue dye that they could get from an indigo, what was called the indigo plant. So, crush up that plant, get its juices out, and soak cloth in those juices, let it dry in the sun, and it would turn blue. I mean, the juices from the plant itself weren't blue, but if you soak them in the, put them on the cloth and then let them dry in the sun, it would turn blue. And it's the same thing with these other dyes that I told you about. There was a purple dye that was from shellfish, a certain kind of shellfish, the glands. So basically you squeeze these shellfish and get the juice out of them, and then soak your cloth in that and let it dry in the sun. It'll turn purple.
And red. And red.
And then, right, in red, this was the insect gut ones. So they found insects that lived on oak trees, and again, you get the juices from them, and I think they added a little honey, and then stirred it up and soaked the cloth in it and let it dry in the sun, and it turns red. So, yes?
For brown, couldn't they use like coffee?
Oh, I'm sure they had others too. Yeah, I mean, you don't want to just I don't know what they used for brown exactly, but these were interesting because they it wasn't as if they just found something that was blue in nature or purple. They actually there was some kind of strange reaction going on here that seemed almost magical to them, because they would get these liquids that were fairly clear liquids, but then when they soaked the cloth in them and let it dry in the sun, it turned colors. So that there was some strange reaction going on that they didn't understand yet, but you can see that discovering things like this, you can see why that in the early stages back then, the chemistry was considered almost a magical subject, and usually it was heavily mixed with religion, and there would the priests, of the tribes would get involved in these various chemical processes, and there would they would have to chant the right things in order to get the bronze from the smelting of copper and tin, say. Now, in fact, the priest chanting didn't really help much. It was the furnace that was really doing the work. But nevertheless, a lot of these early chemical processes became associated with religion, and chemistry is a very, very complicated subject, and there are an enormous number of strange changes that matter undergoes, and in the beginning, when people started discovering some of these seemingly miraculous changes, they didn't have natural explanations, and so they fell back on religious ones. Okay, now the other thing that was going on very early on was, they had discovered, again, practical knowledge of making pottery, and glass. So, again, they didn't really understand the chemistry of what was going on, but they knew that they could shape clay into useful pots and so on, and then if they heated it very strongly in a furnace, that it would harden it up, that it was some change would take place in the clay that would make it very hard and strong. Similarly, by taking things like limestone and soda and sand and mixing them together in certain ways, they could make glass, a clear substance that would that they could see-through that had certain advantages. So, so that was all discovered fairly early on. Actually, glass blowing techniques weren't discovered until about 1,000 years after that. That was right around right around the time of Christ, I guess, that they learned how to blow glass into useful shapes. Okay, so let's quickly move to move toward the present at light speed here. The next interesting discovery that I want to tell you about is 665 AD. It's not known exactly who made this discovery, but somebody discovered something called Greek fire, or at least this is the first year that is known that this material was actually used. Somebody discovered a way to make a certain liquid that would catch fire when it came in contact with water. Throw this stuff into water and burst into flames. Now that turned out to be really useful because you can, how would you use such a thing?
Sea combat.
Yeah, exactly. This was the first chemical weapon. You could, if you were in a sea battle with other ships, you could take, say, some little ship, sail it up close to their big ship and throw this stuff all over their ship. It would catch fire and burn the ship. So this, now what this stuff actually was, it was in effect a combination of a chemical that we now call calcium phosphine. So it's a phosphorus chemical that is actually what reacts with the water and starts the fire. And then the rest of what the Greek fire was in effect gasoline. So they took gasoline and mixed it with this phosphate compound, and the phosphate compound reacts with water and burns, and of course that sets the gasoline on fire. So they had but again, this, you can imagine that for people back at this time, with no real knowledge of chemistry and combustion and so on, being able to create this liquid that, when you throw it into water, bursts into flames. That seemed almost magical to me. Yes.
Did it look right at liquids?
Oh, yeah, there are other, we know of plenty of things today that when you throw them into water. What?
Did it work for just water?
There are probably some other liquids that you can think of that it would work with, but no common ones. For instance, it wouldn't work with alcohol. Yeah.
Why was it called Greek fire?
I think I'm not sure exactly where this was discovered. I know it was first used by the civilization in Constantinople to defend. They were defending themselves against attacks by Arabs. I mean, it may have been discovered in Greece. Yeah, I think this is the only scientific discovery of the 7th century that I'm going to tell you about in this course. Not a lot went on at this time period. Okay, so let's, because not a lot went on then, let's skip to the Middle Ages. And let me just briefly sum up a few things that were known in Europe by 1300. One is that they started, they had discovered distilling techniques. So, in other words, if you want to purify water, okay, what can you do? Well, you can boil it, but use an apparatus so that you boil it off, and then it condenses on the apparatus, and you after it recondenses, you have it drop into another container. So you could start out with water that had a whole bunch of impurities in it. The impurities stay behind in the boiling process, and the pure water comes off as steam, and then you just gather that steam and recondense it, and then the water you get from this, the distilled water you get from this process is pure and drinkable. Okay, so they they knew how to do that in the Middle Ages, and they actually used that technique to make alcoholic beverages too. For instance, you could take wine and distill it and make a liqueur that had more concentrated alcohol in it, and so they could make various liqueurs. Okay. They also discovered 2 different kinds of acids. Sulfuric and nitric acid. Now these were liquids that were highly corrosive, sour tasting, and in concentrated enough form, they even they burn your skin. So they would end up being useful in a lot of chemistry experiments that we'll hear about in the future. But they were first discovered in the Middle Ages. The other thing that actually had been discovered a few centuries earlier in China, but wasn't known in Europe until about this time, was gunpowder. That they learned that if you combined charcoal, sulfur, and a certain extract from manure. Yeah, right. The what is called saltpeter. You can get it from, like I said, you can get it from manure. It's a nitrogen compound, but later chemists would discover. But if you mix these 3 things together, you get this very useful explosive powder. So that, like I said, that was first discovered in China, but Europeans knew about it during the Middle Ages. Now, notice I haven't told you about any real theory here. I mean, about what's going on during these chemical changes, and how to understand all these amazing changes that matter goes through. I think, I mean, at this point they didn't have a theory. They just had these little bits and pieces of knowledge. Now, to the extent that they tried to come up with a theory, the theories they came up with were wrong. And, you know, in hindsight, we can easily look back and see that they were really investigating a very complicated subject, and they didn't have enough information to come up with a decent theory. They tried to identify a few basic elements. See, everybody had the same basic idea when it came to theory. They thought, if we can identify a few basic elements and then explain everything else in terms of just combinations of those few basic elements, then we would have a subject that we could actually understand, that wouldn't just be, you know, a million different things. So, I mean, going back to ancient Greece, remember that the Greeks had taken basically two different approaches to simplifying a theory of matter down to a few basic elements that hopefully they could understand everything else in terms of. There was, do you remember the theories in Greece? Troy?
The one with there was earth, water, and fire.
Yeah, exactly. I mean, there was the four major elements of earth, water, air, fire, and the idea was that everything else is made up of combinations of those. And you could see a little bit about what motivates such a theory. I mean, they had a solid, a liquid, and a gas, and then fire seemed important, but didn't really seem to fit into any of those three categories. So they named that as a fourth one. And you know, this is still this idea that they had in ancient Greece of there being four main elements associated with earth, water, air, fire, is still very influential, all the way up into to the time of Newton. Let's see. So there was one other Greek idea. Daniel?
Atoms?
Yeah. The other idea that the Greeks had was that everything was made of atoms. Now, turns out that that's right. But the Greeks couldn't do anything with the idea. It didn't really arise from any evidence they had, and consequently, scientists couldn't do anything with the idea for a long time until it actually started having a basis in observational evidence. So that all of the attempts at theory up to this point were cases where thinkers were jumping ahead of themselves, that they were trying to come up with the final answer before they had enough evidence to even ask the right questions. In the history of science, that is the main mistake scientists make. It's getting ahead of themselves and trying to jump to the ultimate cause or the ultimate answer before they have nearly enough data to really draw any of those conclusions. So so in effect, there isn't a theory at this point. They're just gathering evidence, but they're still influenced by this idea of earth, air, water, fire. And then in the Middle Ages, there were a few people who started doing some chemistry investigations that suggested that mercury, sulfur, and salt were basic elements out of which everything else was made. But it was all wrong at that point. Now, when did people actually start doing real scientific chemistry? Any guesses? Yeah.
The middle of the 17th century.
Yeah, how'd you know that?
You said Newton.
Oh, I didn't say Newton
You said around Newton.
did that. Okay, you picked up on that. Yeah, that's absolutely
That's
right.
my mom's.
And that actually shouldn't surprise anybody because we've already seen that modern science started in the 17th century. I mean, Galileo really opened the door to modern science, and this was the first time people started doing science the way that science is done today, and the way it's supposed to be done, approaching it experimentally, rather than just speculating and making guesses. So, in fact, that's exactly when the right experimental approach started to be used in chemistry. So, the first guy I want to tell you about is a guy, John Mayau. And his years are 1641 to 1679. Now, so he was born 1 year before Newton, right? And in fact, right around the time that Galileo died. So this is we know we've already learned a lot of what was going on in physics at that time, but let's see what was going on in chemistry. Well, Mayau did a crucial experiment that actually showed people that air was not an element. And let me show you how he did that. He had the idea that when you see a candle burn, that the candle was taking something from the air. Now, well, one of the ways that, I think I already told you, that it was around the time that Mayau was starting his scientific researches that people had invented the vacuum pump, right? And I think I told you that another scientist at this same time showed that if you have a container and you have a candle in the container, of course you can light the candle, it'll burn, but if you pump the air out, flame goes out, right? Candle won't burn without the air. Okay, so, well, that's interesting in itself, that somehow the the burning process is crucially dependent on having the air. It has something to do with the air. Well, Mayo had the idea of taking a glass container okay, so he's got this big glass container that he can invert into, a vat of water, okay? And he's got a candle in here. Now, what Mayo saw was, as the candle burns, what do you think happens here? Any guesses as to what he saw?
Eventually the flame went out.
Yeah, eventually the flame will die out, but before the flame dies out,
The
yeah,
water level of the fat in the glass container rises.
yeah, exactly. This water level goes up. It goes up more than that. Actually, I should have drawn my candle bigger. But as the as the air burns, the water level goes up, and then and then at a certain point, the candle just goes out. But before, all the air is used up. Okay, so it burns for a while, and obviously it's somehow consuming some of the air in this container because the water level rises here. Then, but the candle goes out, and there's still air left in here. Otherwise, the water level would rise all the way up, right? So there's still a bunch of air left in there, but for some reason, the air left won't burn. So what do you conclude?
I heard that if you burn hydrogen, that it becomes water. Did it have to do with it? You need air to make water.
Yeah, I mean that's true. They don't know about hydrogen yet, though. And he's starting with ordinary air here, and he's finding that some of the air is used up in the burning process, but then the burning stops and you've still got a bunch of air left. Troy?
But there are different types of things in the air, and some things.
Yeah, I mean this was the first hard evidence that air was not a pure element, as the Greeks assumed, that it was a mixture of different stuff. I mean, it had to have, in order to explain the results of this experiment, it had to have two components. Part of the air that burns, and part of the air that doesn't. So, what Mayo concludes is air switch markers here. Air is a mixture of two gases, say. Um, one that burns and one that doesn't. And that most of the air is this kind of gas that doesn't burn. Um, okay. I mean, he wasn't able to get too quantitative here and determine exact proportions, but certainly he realized that the vast majority of the air doesn't burn at all. Yeah, true.
So every time you did the experiment over the water level would be at different times because
Well, I mean, he couldn't. I mean, if he had a way, for instance, of lighting his candle, at this point, I mean, it wouldn't light at all after it burned out the first time.
no, I mean like if
But-
you dumped all the water out of the thing
Yeah.
and did it all over again, would the water level be at the exact same?
Yeah, every time I mean, he could repeat this, and it would, would go up to the same level. Yeah.
Couldn't he then,
Well, the reason, I mean, the reason he doesn't get an accurate number for the proportion of air that burns to air that doesn't burn. I mean, you're right. He can obviously measure the amount of volume that is decreased in this container, but he needs other. In order to get an accurate number, he would need better temperature control than he had. There are various sources of air in this experiment that he didn't do too much to control, and so he did not get an. We'll see later that there are some more careful experiments that are done that do get a very accurate value for the proportions here, but John Mayow didn't get that far. But he has proven something really interesting here. Now, he does something else here. He, well, one of the other things he does is he builds a little shelf, let's see, in his glass container here. He's got a hook with so he's got a little platform in here that he puts some sulfur on. Okay, now sulfur is easily burned. If you take a piece of sulfur and you just shine a magnifying glass on it, it will, a bunch of sulfur powder. So it's a yellow powder. Okay, if you shine a magnifying glass on it, it will burn. It'll burst into flame. Okay, well, the Mayow could do this when he starts this experiment. He could shine the magnifying glass through his glass container onto the sulfur, and it would burst into flames. Okay, but after his candle has burned out, he can shine the magnifying glass on the sulfur, and it won't burn anymore. Okay, so that's just another piece of evidence that, yeah, this whatever, there was a component of this air that was essential to the burning process that isn't there anymore. Now the other thing, we've got 1 minute left, but I'll tell you the other very interesting variation on this experiment that Mayow did which was he found out that if he had a mouse in here, that the mouse would live for a while, and then when the air was partly used up, but there was still a lot of the air left, the mouse would die. Okay. Now, Mayall proved that the mouse was breathing the same part of the air that supported burning, and that the mouse couldn't breathe the other part of the air. So for the first time, there's this connection between combustion, the part of the air that burns, and the part that we actually use in breathing. It's the same part. The rest of the air is useless for burning and useless for breathing. And Mayall showed that by putting mice in there that died for a good scientific cause. Okay, so we'll pick that up this afternoon.